Hello, so let's talk a little bit about the normal force. So we're going to consider a person standing in an elevator that is accelerating upward. So it's not just standing still, it's accelerating upward. The upward normal force exerted by the elevator floor on the person is larger than the weight of the person, identical to the weight of the person, or smaller than the weight of the person. Alright, so here's the deal with the normal force. The normal force is a force. It's not necessarily directed up and down. You can have horizontal normal forces depending on the circumstance. But for the most part, when we're talking about a person standing still, if they're not accelerating, if they're not moving up or down, the normal force exerted by the floor on the person is equal and opposite to their weight. Now we have a case where the floor is the floor of an elevator, and that's exerting a force on the person that is not only equal to their weight, but it's bigger than that because the person and the elevator floor is accelerating upward. So the answer is larger than. Let's look at an image here. So we have this dude standing on an elevator. The dude has a weight of 700 newtons. They're standing on a scale on the elevator. This scale is reading their true weight, 700 newtons. And that scale is telling us exactly what the normal force is. That's what a scale does. It tells you what the normal force is that is being provided, equal and opposite to your weight. So now, this person is standing on the elevator, presses the button, the elevator starts accelerating up, and the elevator is providing more than their true weight. It's providing extra upward force, 1,000 newtons. So we could actually figure out what the acceleration is. Acceleration equals force equals mass times acceleration. Acceleration equals force over mass. So we could figure out this person's true mass. It's different than their weight, right? Weight equals mg. Mass then equals the weight divided by g. So if we rounded g to be 10 meters per second squared, we could say this person has a mass of about 70 kilograms. And since the net force on this person, 1,000 newtons minus 700, there's a net force of 300 newtons directed upward, acting on this person's 70 kilogram mass, we could figure out what that acceleration is. Here in this case, the elevator is accelerating downward. The person pressed the down button and the elevator accelerates down. When you hold a pen in your hand and kind of drop your hand out from underneath it, that's essentially what an elevator does. Maybe more often on the Tower of Terror at an amusement park, but that's essentially what the elevator is doing. It's letting you fall down a little bit. So in this case, it's only providing an upward normal force of 400 newtons compared to this person's true weight of 700 newtons, and the net force is negative 300 newtons. 300 newtons directed down toward the center of the Earth. Now in this case is a bad day. The elevator cable has snapped, and this person is plummeting to their death. But when they look at the scale, it reads 0. That's what weightlessness is. That's what weightlessness in outer space, the people that are on the space station's in orbit around the Earth, that orbit is kind of due to the idea that it's constantly falling down. It's moving horizontally, but it's always falling down toward the surface of the Earth. That's the sensation of weightlessness when they're in orbit. So the upward normal force is 0, even though this person's true weight is 700 newtons directed down, because they're moving down with an acceleration of 9.8 meters per second squared. Alright, so the true answer was, for accelerating upward, the upward acting normal force is larger than their true weight. Alright, so is a net force being applied to an object when the object is moving downward with a constant acceleration of 9.8 meters per second squared? The net force. It's force up minus force down. Wait, net force equals mass times acceleration. This thing is accelerating. If something is accelerating, there is a net force. Is a net force being applied to an object when the object is moving downward with a constant velocity of 9.8 meters per second? If an object has constant velocity, then the acceleration is 0, in which case there is no net force. The net force is 0 if something's moving with constant velocity, whatever the situation. Alright, so if there's no velocity, there's no acceleration, so there's no force. Whoa, it's a tug of war. Whoa, they're pulling back the other way. And again the other way. How often do I go on? It's not that there's no force. The force to the left here equals the force to the right, and so they're just stationary. Means there's no net force. Means the net force is 0. This is a great tool in the world of physics. So sigma F, the sum of all the forces, if this equals 0, and it's always equal to 0 if there's no acceleration, if there's constant velocity, then we have this great tool, we have this insight that we can figure out something about the forces going on in different directions. Alright, I've kind of hinted at this, now we should mention it. Newton's third law of motion: whenever one body exerts a force on a second body, the second body exerts an equal and oppositely directed force. I'll be equal, I threw an equal twice, on the first body. That's what we're saying with the normal force. If I'm sitting here in my chair, there's a downward acting force acting on me. That's my true weight. Then there's an upward acting normal force. When I exert a force on the chair by pushing down on it, the chair exerts a force back on me, pushing back up on me. That's Newton's third law. When I throw a baseball, I exert a force on the baseball, but the baseball exerts a force back on me. Alright, that's enough for right this moment.